we are introducing AF2S3Net Attentive Feature Fusion with Adaptive Feature Selection for Sparse Semantic Segmentation Network, introduced by Ren Chen, Ryan Razani, Essen Tagavi, Inshu Li, Bingbing Liu from Huawei NoSARC Toronto office, Canada. Semantic segmentation is a well-explored research topic in 2D RGB image domain. However, doing semantic segmentation on point cloud has recently become popular thanks to the quickly development of the autonomous driving industry, especially thanks to the release of two well-known datasets, Semantic Kitty and Nuisance. The sparsity property of a point cloud makes this task much more challenging. Also, due to the lack of color feature, we cannot depend on our perception on the rich texture information. The only information we can use is the geometric information of the 3D points and their intensity. Thus, we want to find a better model that's designed perfectly for the sparse dataset and at the same time fully explore the 3D geometry. Luckily, an AutoDiff library designed for sparse data introduced by Stanford Vision Lab, named as Minkowski engine, perfectly fit for this problem. Sparse convolution was initially brought from 2D image realm, where they do sparse convolution on submanifold. Namely, the convolution output will be counted only where the kernel center covers its input side. Likewise, we can extend this idea on 3D data. Instead of introducing 3D kernels to slide through the voxel grids, we squeeze the data into a hash map and perform convolution by quarrying the neighborhood. The feature of current point is projected into the submanifold first, and then aggregated with neighborhood. And this convolution kernel weight matrix was updated only if the corresponding neighborhood offset has elements. This special design fully explored the 3D spatial information, whereas limited the growth of the computation by skipping the empty neighborhood. Our sparse 3D neural network is designed for better exploring the spatial context information using the sparse convolutions. The structure contains two major parts: Attentive Feature Fusion module, named as AF2M, and Adaptive Feature Selection module, named as AF2S3Net, where the two modules will be covered in the following slides. Here, AF2M is a multi-branch structure combined with attention feature fusion. AF2S3Net is a squeeze excitation module used to filter out the redundancy introduced from the multi-branch output. Before going into details of the modules, let's first navigate through the overall pipeline of this network. One frame of 3D point cloud is first converted into a sparse tensor, which contains the coordinate list and the corresponding feature vector for each voxel cell. The sparse tensor then gets fed into the AF2M multi-branch spatial feature extractor. At the same time, the feature extracted by multi-branch are filtered by AF2S3Net and got concatenated with the last transpose convolution layer. Inside this network backbone, there are convolution blocks and transpose convolution blocks. Each convolution block contains 3 layers of convolution, and transpose convolution block contains 1 layer of a transpose conv, followed by 2 layers of the convs. Please note that all the layers inside this framework are sparse layers, which is specially designed for the sparse tensor. The last convolution layer finally converts the submanifold features into semantic class probabilities, and then those probabilities got maxed to recover back to the semantic classes. Now let's start with the AF2M Attentive Feature Fusion module details. Heavily inspired by two influential papers, Bilateral Semantic Segmentation and the Adaptive Feature Fusion modules, the Adaptive Feature Fusion module uses multi-branch that captures the detailed information and highly abstracted semantic information. And then we use Adaptive Feature Fusion to aggregate the feature across branches. Unlike feature fusion in image realm, which requires a resize that might introduce the extra error and computation complexity, sparse tensor has the internal hash map across the scale space that can be easily updated with little effort. In AF2M, we use a broadcast operation to match the attention of feature vectors with the original sparse tensor output, x1, x2, and x3 namely. Please note that the attention layer H is the attention layer which compresses 32 columns of feature vectors into a single column feature vector. which is equivalent to the single-channel attention map in the image domain. The broadcasted attentional feature scales the original output pointwisely, and then they are linearly added. This way, with the detailed pointwise feature are passed through the shallow branches and get blended into the deeper semantic branches. Here is an intuitive illustration of what is going on with AF2M. Pointwise shallow convolution memorize the fine-grained detail features and pick up the small objects, for example the traffic sign, pedestrians. And the larger kernel with deeper branches cover the larger area of the receptive field and hierarchical informations that can differentiate the difference of each kind of vehicles. For example, the trucks and for example the bus, right? All this information are linearly fusion, creates rich detail and context feature for upcoming layers to reshape their submanifold. Given the multiple branch input triple the network width that might contain many redundancy, we found that simply forward and concatenate them into the decoder layers will confuse the decoder network and decrease the convergence rate. Thus, we introduced the adaptive feature selection module as a channel filter to filter out those redundant feature columns. The sparse interchannel attention module is much more like a squeeze excitation, where all the point features are aggregated into one row of a feature vector by a spatial global pooling layers. The aggregated feature vector is compressed and decompressed by a fully connected MLP. Then the single row feature vector is filtered with the pointwise convolution afterward. Each column of this 1 by n, which is 64 here, feature vector is multiplied back into the sparse tensors feature map to emphasize the sparse tensors features column-wisely, which is the channel-wisely, for each point. We observed gradient vanishing after introducing the submanifold and sometimes result in divergence. To eliminate this artifact, we introduce a damping factor theta, which takes the original data as a basis and offset. The scaling effects of the squeeze excitation can only affect the offset, and we can adjust the contribution of the submodule by adjusting the theta value. In our experiment, lambda is empirically set to 0.35. Our customized loss function has two major components. One, the weighted cross-entropy. Two, the local GeoAware loss. We define a local GeoAware term by calculating the neighborhood anisotropy of current point and pointwisely scale the entropy of each point. The anisotropy is defined as 0 if the class label is equal to the neighborhood, and 1 if they are not. When the network has a higher confidence on the semantic predictions, the major area contributing to the error lies on the boundaries of the semantic classes. This local GeoAware term has large value around the border and diminishing the effect of the center of each semantic area, which is geometrically equivalent to the focal loss. Upon this talk, our method is still ranking first on both Semantic Kitty and Nielsen's benchmark. Here is the qualitative result of our method. Please note that all the methods are inferred real-time. Thank you.